Question D. How could you construct or install the main cable? So we can install the main cable by shooting a small cable first across the valley to the other pier. After that, you can use that small cable to string other cables back and forth across the two piers, and then we can attach all these small cables together to form a large cable that can hold the weight of the whole bridge. So one unanticipated difficulty that we had was that the placement of the pins on the blocks to form the main span of the bridge were weirdly placed. So the blocks kind of locked into each other and one part of it was below the other. So this meant that when we were building the main span of the bridge, we had to build from one side of the bridge to the other. So this is kind of unexpected, as when we tried building from both sides inwards, the cables were balanced, but we couldn't get the blocks to balance on one side of them because of the placement of the pins. However, in real life this wouldn't happen, because we would build from both sides inwards to balance the cables so that the cable wouldn't be deformed. And for the second part of the question, we put the block with a green dot on the side of the pier, so this meant that the block wouldn't be suspended by the cables, and this would make the side of the pier more similar to a beam bridge. Yeah. Question F. Loads in a real bridge. So first of all, we have the weight of the bridge deck itself. These would be body loads, and they're also internal and static, meaning that they don't move and that the forces arise within the bridge itself. Second, we have the weight of the traffic lights and the fences. These would be external forces relative to the bridge itself, and they're also static because they don't move. Third of all, we have the weight of the cars and of the people traveling over the bridge. These would be external forces, and they would be dynamic because they would be changing. You don't know the amount of people or cars that would be on the bridge at any given moment in time because it would change. And last of all, we have wind, rain, or snow loads. These will also be external and dynamic. So the load of the bridge deck and the load of the cars on the bridge would be transported to the cables, and the cables would then transport the loads to the towers.
So the tension in this main cable would be equivalent to the weight of this deck here. And so the equation could be force equals mass times acceleration, where the mass is the mass of the deck and the acceleration is equal to gravity. And so this is tension, and the ratio would be 1 to 1.
What would happen if we removed just one of the two? Let's say this one. If we apply that same vertical force downwards at the center of the bridge, then there is no longer any friction that opposes the horizontal force, and so there's nothing to stop it from moving horizontally and therefore concave inwards.
The positions of the towers can be established by using laser measurement with the use of a total station. A total station can be set up on one of the banks of the river, and the surveying partner can use a boat to travel to where the expected base locations are to be. The total stations can take shots at the prisms, and ultimately by utilizing the UTM system, or the Universal Transverse Mercator System, can locate the exact location of the prism with coordinate points. The processes can be repeated until the correct coordinates are located, and the difference of the two coordinates at each base will equal the desired span length, in this case 1 kilometer. Once the cable has been installed on the span, the next component to go in is the actual bridge deck. The way the deck can be built is a barge can transport the pieces across the water, all the while an actual crane can run along the completed portions of the deck. For instance, in portion 1 and 2, position 3, it can carry up the next piece to be installed at this location. The process can continue all the way until the whole span is complete. As the truck drives across the bridge, the joints along the deck flex. At the joint where the weight is exerted, the two pieces tilt inwards, ultimately displacing the rest of the bridge, similar to a sinusoidal function. In order to solve this, a piece of plywood should be added to the deck to make the deck more rigid, similar to a real bridge.